And here we have the notes for section 1.3, exponential functions. So there's our objectives up there. All right, so exponential growth. So an exponential function has this form: f of x is equal to a to the xth power, where a is a positive real number that's not 1, because if it is 1, then the equation just equals 1 forever, because 1 to any power is 1. The a is referred to as the base. So down there below, you have the domain of the function is negative infinity to positive infinity, which means that you can plug any value in for x that you like, but the range is from 0 to infinity. So it is impossible to get a negative number using an exponential function, assuming a is positive. All right, so example 1 here, graph the function and state its domain and range. So I'm just going to let the calculator do the graph. Hopefully it'll show up here. Oh, there it goes. All right, so we'll go down to graph, and the equation is 2 quantity 3 to the x, closed quantity minus 4. Draw. Yep. So there's your function. It's that lovely little spiky line there. So the question says, we'll move it over here, state the domain and state the range. Well, from up above, the domain we know is all real numbers. So negative infinity to positive infinity, or you could just do all reals. The range is a little bit trickier. Now this 0 to infinity is only the range if you don't have any other crazy stuff, like we have this minus 4, and we have that 2 out front, things like that. So the range is the y values. So this graph goes up forever, so it's going to go up to infinity, but it will have a lower value. If you look here at the graph, it flattens out here at negative 4. So negative 4 is actually the lowest value that the graph can take. Or you could write it as y must be greater than negative 4, if you wanted to write it that way. Okay, so the second one here says find the zeros of that equation graphically. So we'll get our graph back here. So we'll change our equation, 5 minus 2.5 raised to the xth power. Draw, so it looks like that. So we need to find that value there where it crosses the x-axis. So there's one of two ways you can do it. You can use the trace command and try to kind of approximate it. So it's somewhere between, so there's positive, so x of 1.6 has a y of 0.6, and if I go to 1.8, so it's somewhere between 1.6 and 1.8, so probably about 1.7. On a Casio, if you press F5, G-solve, and select root, it'll actually give you the exact value, so I was right, it's about 1.75. 6 if you round it. Alrighty. So over here, we got the rules for exponents. So just a couple of reminders. So if you multiply two values, you add their exponents. If you divide two values, you subtract their exponents. If you raise a power to a power, or reverse order, doesn't actually matter, you multiply the two exponents. In this case, if you have two values both being raised to the same power, you can multiply them first and then apply the exponent. And the same thing here happens for division. If you are dividing two numbers, now remember, sorry, if you're dividing two numbers, you can distribute the exponent. Remember, these things also all work in reverse. So if I have something like this, I can rewrite it like that. If I have something like this, I can rewrite it like that. You can read these right to left. All right, so exponential decay produces a decrease over time. Radioactive decay is the most common of these. So the half-life of radioactive substance is the amount of time it takes the substance for half the substance to change from its original radioactive state to a non-radioactive state by emitting energy in the form of radiation. So for example 3 here, suppose the half-life of a certain substance is 20 days and that there are 5 grams presently. When will there be only 1 gram of the substance remaining? So this is the generic equation. So y equals y0, and then 1/2 raised to the n, where n is equal to the number of half-lives. So we will have to do one conversion at the end to convert half-lives back into actual time. So y is our current amount, so 1. We started with 5 raised to the half to the n. So the first thing you need to do is divide the 5 across, so that's 0.2. It's equal to half to the n. Now to get n out of the exponent, we have to use the natural log. So if we take the natural log of both sides, we can actually rewrite it so that it looks like this. When you take an exponent inside of a log, the exponent actually comes out front as the coefficient, and then you have the rest of it. And then I can just divide. I'm going to actually switch to all decimals because that's, whoops, that should be 0.2. This one will be 0.5 equals n, and that can go in my calculator. So natural log of 0.2 divided by the natural log of 0.5 is 2.3. So n is about 2.3. But that's the number of half-lives. So I need to multiply that number by 20 to get the number of days. All right, so down here, we've got growth and decay, so it gives you the general form here. So k is a positive number for exponential growth. No, k is greater than 0 is a model for exponential growth if a is greater than 1. So this part here actually applies to this, or k has to be a positive number. So if your number here that has the exponent is positive, it's growth, or more than 1, sorry, it's growth. If it is between 0 and 1, it's decay. So like up here, that has a half. Now the reason this is a half-life is that we're keeping track of how long it takes half of the stuff to disappear. If we knew how long it took a quarter of it to disappear, this would be a 1/4 in there. Or if we knew how long it took to double, that would be a 2. But that'd be a growth problem. All right, so on the other application of this is compound interest. So here's the formula for calculating the amount of money in an account. So you can put an A over there if you want to know the value of the account as an equation. So P is the principal, the beginning amount. R is the interest rate as a decimal. N is the number of times it's calculated per year, and T is the time in years. So down here, example 4, Bernie deposits $2,500 in an account earning 5.4% annual interest. Find the value of the account in 10 years if the interest is compounded annually, quarterly, monthly. So for annually, n is 1. You do the interest once a year. For quarterly, n is 4. 4 times a year makes a quarter. And monthly, n is going to be 12. Now the equations are going to set up real similar. So for this one, a is equal to 2,500, the starting amount, 1 plus 0.054, you have to convert your percent to a decimal, and n is 1. And this is going to be raised to the 10th power, because it's n times t, n is 1, and t is 10. Now that can all go in your calculator at once. So 2,500, 1 plus 0.054 divided by 1, all raised to the 10th power. So this is $4,230.06. For down here, for quarterly, almost everything's going to be the same, except n is now 4, and this is now 40, because it's 10 times 4. So 2,500, 1 raised to the 40th. So this is $4,274.55. And then lastly, 2,500, 1 plus 0.054 over 12 raised to the 120th, 12 times 10. Between decimals. Divided by 12 raised to the 120th. So this is $4,284.82. So as you see, as you calculate your interest more often, the value in your account increases. So you start at, that's a 0, not a 6. 30, 42.30, then 42.74, then 42.84. Now the other thing you can have is a continuously compounded interest. So this part here is the part of the formula here. It's 1, whoops, it's off the screen, 1 plus Rn to the nth. So that all reduces just this number e to the rth power if you let n get super duper large. Like you keep calculating interest more and more and more and more often. So as n gets ridiculously large, you can simplify the formula down to this. So the interest rate just becomes this equation. That's referred to as compounding continuously. All right, so last example here. So once again, we're going to do daily and then continuously. So daily is going to use the old equation. So 2,500, 1 plus 0.054. So daily n is 365, and this is going to be 3,650. So 2,500, 1 plus 0.0 divided by 365 raised to the 3,650 power is equal to $4,289.85. Now continuous has a different formula. It looks like this, PERT. So it's going to be 2,500 times e to the 0.054 times 10. But that can still all just go in your calculator. If you're looking for the e key, you normally have to hit shift or second and then your natural log button. So this comes out to be $4,290.02. So So it's not a really super giant increase over this, but the longer you let the time run, the more these numbers will start to drift apart. I'm sorry. And that is the end of this section.